introduce our third guest lecturer, Professor Gary Cardi from University of South Africa. He's with me at the Department of Mathematics. I don't know if you've seen our beautiful Florida Science Campus. If you ever do go in that direction, please come and visit us. And this evening he will be introducing you, for some of you for the first time maybe, matrices. I'm not sure how many of you know even what a matrix is, so this is exciting. And there's some applications of the Kronecker product. So over to you, Mary, and thank you.
Good evening, and well done for making it this far. Firstly, I'd like to just get an idea of how many of you know what a matrix is. So that's quite a few. How many know how to do matrix multiplication? So that's good. Okay, so you don't need to know what a matrix is. I'll try to tell you. And you don't need to know anything about matrix multiplication. I'm going to introduce it in a very complicated way. I'm going to do so via the Kronecker product. The Kronecker product is an interesting product of matrices. I use it quite regularly in my research, but it's relatively simple to understand. So we'll try to build on those ideas. I'll give you a short tour of some basic matrix products, how we can use them, and then at the end we'll hopefully get to the matrix product. And that's the usual matrix product. Right, so from the Oxford English Dictionary, a matrix is, if you look at definition 7, a rectangular array of symbols or mathematical expressions arranged in rows and columns, and then treated as a single entity. That is the algebraic form. I'll show you a little bit of that as we go along. And there are some other definitions. Most of them are not so relevant. You might know this one, we'll see in a moment. And 4a is also particularly useful. It's about the relationships or the interconnectedness of information in some system. So some of you might know this view of the matrix. This is not the matrix because here we have gaps. So this is a matrix. This is an example of using a matrix to do a very simple encoding, which is what the previous slide was supposed to be. This is going to get you in trouble if you try to use it for secure communication. It's well known, it's very easy to break, but it's still interesting to look at. So this is the interrelation between rows and columns. We've got the letters of the alphabet. We can't fit it on the slide, of course, but it's A through Z. And we want to encode a word, in this case matrix. So what we do is we look up in the first column, there's the M, and we look up for the rows, for the mth row, and if you look in the first column, you'll see it's all in the same order, ABC, from the beginning to the end. So we'll find M at the nth place. Then in the second column, we have an A, and we look up in the A row, in other words, the first row, and we see a B, so the second letter in the encoding must be a B. And so you go on. The ones that are easy to see are the last one, X. I think, no. So if we get to T, that should be a relatively easy one. Right. So what happens is, as you can see from the first column, there's no change in the letter. In the second column, you shift it on by 1. In the third column, you shift by 2. So for T, we go on to U and then V, so that is where the V comes in the third letter. So this is called a Vigenère square, and it's a very old form of cryptography. Other places where you would use matrices is coordinates in space, X, Y, and Z. Coordinates in space-time, X, Y, Z, and T. And you can see there's different sizes. Or maybe, for example, here we've got the exchange rate between the rand dollar and euro. Of course, we could choose which one we want to use as the basis for this comparison. But this is a collection of numbers according to dates. And so the rows can be the dates and the columns can be the exchange rates, the relative exchange rates. We can also use matrices to describe graphs. So here we have a graph. It's got a number of nodes labeled X, Y, U, V, and W. And then if we order those nodes in U, V, W, X, Y, you see there the columns refer to the different nodes and also the rows. This is an example of a directed graph. So we can see, for example, from the node U, we can get to the node Y. And so if we look at the first row, we see U, the first row, and Y, the last column. There is an entry 1, which indicates that we can get from U to Y. All the other entries are 0, so from U, you cannot get to any other node. You will see there's a line between U and X, but it's going in the other direction. We can represent directed and non-directed graphs this way. If it's non-directed, we just take the direction to be both ways. So matrices are very useful for graphs. There's a big industry of research around using matrix properties to describe properties of graphs. Matrices also pop up every day for pictures. So for example, this that you see on the screen, there are colors, there are black spots, there are white spots. And of course, we can encode this. Whether there is a black spot or not, this would be a 1 or a 0, for example. Or how black is it? So we can have a number between 0 and 255, for example, or something like that, to measure the different levels of color on the screen. Of course, we have different color channels. So here we have some red and some blue and black, and we might want to distinguish between all of them. That I'll explain a little bit about later. You can do this via the Kronecker product, but we won't go into too much detail on that now. And the famous Google search. So this is a famous example where matrices were used. Everybody uses Google, I think, probably. So what you do is you represent the interconnectedness between web pages. Say, if somebody clicks on a link when they're searching for a certain term, that takes them to a web page, you record that they've clicked on that link. And you count how many times people click on certain links based on certain search terms. And this creates an array of search terms and web pages. And so you can look at the relationship between search terms and web pages. There is a famous mechanism for this, which is the singular value decomposition. We won't describe it here. It's a little bit beyond the scope of the talk. And that will tell you the relationship between search terms and web pages. And that is actually the mechanism that Google uses, although on the scale that they use it, it's quite difficult to do. So what can we do or compute with matrices? Here we're going to look at the computational aspect. I'll give some concrete examples and a few algebraic properties. So we might want to be able to add matrices. Here's two matrices. The first one has 1, 2, 3 in the first row and 4, 5, 6 in the second row. And then the second matrix, as you see there. And what we do is we add them entry-wise. Okay? If we add them entry-wise, that means that the number of rows and number of columns has to be the same between the two matrices. This is the simplest way to define addition. There are other ways that we could define addition. They would have very different properties, and this is the most common way that we do. Okay, so that's relatively simple. What is interesting about addition is perhaps this zero matrix, a matrix with all zeros in it of the same size as the matrix that we're adding to. It doesn't change the result. So if we add 1, 2, 3, 4, 5, 6 to this matrix with all zeros, we get exactly the same matrix again. So this is an important property that we look for to identify invariance. And it tells us a little bit about the algebraic structure. So if we know about the zero matrix, we can talk about what can we do to some matrix to get to the zero matrix. And this is the negative of a matrix. So here we have the negation of the matrix 1, 2, 3, 4, 5, 6, and all we do is entry-wise negation of the numbers. So that's straightforward. Because addition is entry-wise, the negation should be entry-wise. That follows quite naturally. And then a few properties in algebraic form. If we add two matrices A and B, it doesn't matter in which order we add them. So we can add A to B or B to A. So the direction doesn't matter. If we add three matrices, it doesn't matter if we add the first two and then the third, or we can add the last two and then add the first. And this gives us the same result. Of course, all of these are quite obvious because we are doing entry-wise operations. That means that we have all the standard properties of the real numbers at our disposal. So these properties that you see here follow directly from the property of the real numbers that appear in the matrices. So let's try some multiplication. If we do entry-wise multiplication, then the same properties hold in a sense. What you do is you multiply the first row, first column with the first row, first column of the second matrix, and you get the result. This is straightforward. This is called the Schur or the Hadamard product. It's not the product that you usually see. It does play a role in certain applications, and later on I'll mention another product which is closely linked to this one, but we won't go into it. Which does play an important role with data analysis of large data sets. Oops. I already gave all the secrets away, but let's go back. So what we would like to know again is invariance. So is there some matrix that we can multiply with this matrix, 1, 2, 3, 4, 5, 6, and get the same answer, 1, 2, 3, 4, 5, 6. And that's very easy to see. It's a matrix with all ones in it. Okay?